should I start sharing or?
Yeah, share your screen and go ahead.
Is my screen visible?
It is now.
And I'm still seeable, right? You still see me?
Yeah, I can't see your camera, but I can see your screen.
Is there?
Yeah, now I can see
You can see
you and
both
I
now?
can see your screen. Yeah, you're all set now.
Okay. All right, so today we're gonna be talking about mutant I507 Del by myself, Brian. Okay, so first I want to talk about the whole CFTR process from the beginning. And then, so in order to start, we need to have the CFTR encoded somewhere, which can be found in the DNA in the nucleus, which, and then it later has to be transcribed from DNA to mRNA, which is like the little process right here. And then once it is transcribed, it later has to go through nuclear pores and then into the endoplasmic reticulum, where then uh, it is later passed through nuclear pores and in the and oh yeah, oh, shit. Sorry. Okay, so once it is done with the endoplasmic reticulum, it is then greeted by ribosomes, which create it into the protein itself. And once it is the protein, it has to go through the Golgi, which is the Golgi apparatus right here, where it is then coated with sugars, and later on, it is um, it has to go through a series of vessels around here, and then it ends up in the final destination, which is the plasma membrane. Okay, so for the mutation itself is going to be I507del, and it is a class 2 mutation, which is right here, and it is homozygous. The type of mutation of itself is a deletion in the amino acid, which uh, occurs during the transcription process of DNA to mRNA. And then the cause is a copying error, like I mentioned earlier. It's when it happens in the transcription process. The transcription error results in the wrong amino acid being incorporated into the protein. Some problems that this causes is the protein being misfolded. And right here, there's an image of folded protein versus unfolded or misfolded. And then some problems with the misfolded protein is that it could cause various and a variety of severe diseases, one of them being Alzheimer's and Parkinson's disease. In order to avoid those, we have to get rid of the misfolded protein, and this is done by the protease, which is why I have like a little destruction of the atomic bomb or whatnot, because the protease are enzymes that kill protein. So we have to do that in order so we don't get like sick and get diseases. Effects that this mutation has on lungs is that it creates a thick layer of mucus in the airways of the lungs. So on the left side of the picture, you see healthy lungs, and the airways are like very open and clear, versus on the right side where you can see like it's the airway is really clogged and small, not letting not letting enough air get to the lungs. The result of this, as you can see on the left, the patients that were less than 10 years old, their lung, how do you say it? Only 72 to 122% of their lung is working, and patients from ages 10 to 20, only have 43 to 117% of their lung functioning, while as they get older, it starts to decrease. As you see, if you're greater than 20, only about 30 to 109% of your lung actually works. And then this is just because of the whole mucus stuff. And as you get older, you just get harder to breathe. And then it can result in death. And most deaths are either in mid-20s or higher. And then for effects on the pancreas, it shuts down the whole pancreas, and only about 11% of the pancreas actually ends up working. With that being said, effects that the protein has on the structure, the protein cannot be built due to the wrong amino acid being incorporated. That's why I have like the house that didn't finish, because you just can't. And then effects that it has on protein function, it can't function since it's the incorrect shape, and it doesn't have the ability to build that 3D shape that it's supposed to build. That's why I have the block going into the wrong hole, because it doesn't function. Some solutions for this mutation. I wasn't able to find cures. However, I found treatments, and one of the treatments is Symdeko. And Symdeko is basically I would say like two medicines, and one of them is the Ivacaftor, but we don't really need to worry about that one right now. Right now, we got to focus on the Tizacaftor, and that's basically, it brings more protein to the cell surface, which is what we need since we don't get protein at all, since it's not created properly. In conclusion, the mutation is very severe since it causes many side effects. Some of the side effects would be wheezing, coughs with phlegm, digestive problems, the lack of not being able to absorb as much nutrients, and the protein, like I mentioned, since the wrong amino acid is incorporated, it's not functionable. It's basically just like a whole waste. And yeah, symptoms are very severe. And even though the function, even though, like going back to the pancreas, even though it kills most of the pancreas, you can still live. And that's proven like through modern surgeries, where you just have to adapt and change your lifestyle a lot, but you can still survive. And as for the lungs, you can also still survive, but the chances are very, very low as you get older. And then that's my works cited, and yeah, I'm finished.
Okay. Any comments or questions for Brian? In that event, let's go on to group 8. Group 8, would you like to proceed?
Yeah, let me share my screen. Wait.
We can't hear you, I think.
Can you hear me right now?
Yeah, I can hear you.
Yes, yes.
Okay, let me. Okay. Oh, yeah. Can you see my screen now?
I can see you, and I can't see your screen, however.
No? You can or
I
you
think you
cannot?
can see, we can see your screen. You just have to get out of the cameras of the call, of the Zoom call.
I don't know. I don't know why this
You
happened.
have to like when you press share, you have to click desktop, and then you have to click the image itself, what it's showing.
It only gives me 3 options. One says Chrome tab, and then another entire screen in window. And then I click on the one that says Chrome tab, but I don't know where, you know?
Now you have Brian, now you have me.
Can we go to the next group and then I will try to fix this?
You can try clicking view to get out of full screen on the right hand corner.
Where?
After you start sharing your screen, there is still a thing that says view with like a little box.
No. Oh, let me. And then full screen. Now you can see it or no?
Yeah, I can see your name on the screen, but now I can't.
But the presentation, you cannot see it.
It might be are you using the Zoom application?
Yes.
It might be that, but in that case, I'm not sure what to do.
I think when you click the share screen, yeah, now see it.
Yeah, now we've got your slide. Yeah, looks good. You're muted, Bianca.
Can you hear me now?
Yeah, now we can hear.
Okay, so my name is Bianca and we will be presenting about our mutants. So first I will be explaining a little bit about cystic fibrosis, and it's caused by mutations on the cystic fibrosis transmembrane conductance regulator. And it's a hereditary disorder. Sorry about my pronunciation. And cystic fibrosis causes several damages in the body, primarily in the lungs and the pancreas. And then another important thing about cystic fibrosis is that it's a common genetic disease on children. So now moving into our mutant, which is N1303K. So this mutant is a pancreatic ducts and sweat glands, and this type of mutation is common to we can see it right here. This mutant doesn't have channels because it stops right outside the nucleus and never get close to the plasma membrane. And on this mutant, nothing gets to the cell surface. And also proteins never gets to the membrane, and it never gets past to the Golgi. So now moving, so Amar, can you talk a little bit?
Do you guys see me? Yeah. Hello?
Yeah, we can hear you.
Okay. Is it cool if I just leave my camera off because I don't have that well of a service, so I don't wanna be like cutting out.
Well, it's fine just the way it is now. We can see you talking and we can also see the full screen.
All right, cool. So the effect on the N1303K mutation on the protein structure So it's a protein processing mutation where the CFTR is made, but the cell doesn't go through. Like we had said, the channel is closed. And on the top right, as you can see that there's a fold increase on the mutation. You can see the bar go up on the top right. So it causes defect, biogenesis, and gating abnormalities of the CFTR protein. It also has mutations disrupting the ATP hydrolysis or MBD dimerization fail effect. So it just is basically saying that the channel gating is closing down and it's hard for plasma and cells to get to the surface. And that's the main effect on the protein structure that the mutation has on a patient. Can you go to the next slide, please? So the CFTR protein is created, but it misfolds, keeping from the cells moving to the surface. So as you can see on class 2, there's no trafficking, and there's an image right there showing how the plasma doesn't get to, I believe that's mitochondria. I don't know. And there's also correctors such as lumicaftor, if I'm pronouncing it right, and it helps it be a more defective CFTR fold. So it helps it fold more correctly in order for the plasma and the cells to get to the surface. The potentiators are some drugs that can help the CFTR channels, and it can also help the plasma or the cell rise to the surface, and it increases the chloride transports. You can go to the, yeah.
So some symptoms, signs, and complications caused by N1303K mutations. So like I said before, this causes severe pancreatic insufficiency, form of cystic fibrosis. Some other symptoms are salt-tasting skin, respiratory problems, lungs infections, and weight loss. I make this picture a little bit bigger so you can see it better. But this is a clear example of a healthy airway and then a airway with cystic fibrosis. And Amar.
Yeah. So there are cures and there are treatments for this mutation for the patients. There could be some correctors, such as a combination or a lone corrector, which it boosts the mutant and it's beneficial, such as where's the corrector at? A C4 and a C18 and a VX809. It can increase the CFTR chloride channel function on both of the functions. There's an improvement of trafficking function so that the plasma membrane can have cell access, and it reduces the association with the autophagosomes. The mutation is also classified as a severe mutation causing pancreatic insufficiency, and it does cause diabetes mellitus, and it's associated with pneumothorax in the lungs. So it does give you breathing problems, and these treatments and other antibiotics can increase the channeling so that your lungs can get enough plasma membrane or like cells. On the image to the right, as you can see, there are the correctors or the combination of mutants, and then that's it.
So this is our work site, and that's all we have.
Yeah, I'm curious if you look at the next to the last slide, what's the The image of the people from the baby to the old man, what is that showing?
Oh, I just add that picture, but it's like it's not like explaining the cures or the treatments. It's just like explaining that it's a hereditary disease. That's my explanation for that picture.
Okay, all right, good. And that's the end of your presentation.
Mhm.
Okay, thank you very much. Are there any other questions from the class about this presentation? Okay, thank you.
Mhm.
And we go on now to group 9.
Can you see? Can you see the presentation right here?
Can you guys see and hear us?
Yes.
Yeah?
Yeah, we
Okay.
can see you guys.
Okay.
Can you guys see yourselves right here by the presentation?
I can
Yes.
see
Yeah.
your images.
Okay,
Yes.
let me see if I can change that so you won't be like staring at yourself.
Is the time running?
There we go. Oh, is the time running right now?
Yeah, time is starting now.
Okay. Okay. Hi, I'm Sasha.
I'm Elizabeth, and our mutation is R553X. Sorry, go ahead, Sasha.
Okay. Okay, so what is a genetic mutation? According to nature.com, mutations are changes in genetic sequences, and they are the main cause of diversity among organisms. And these changes occur at many different levels, and they can have widely differing consequences. And some things that may cause these mutations include exposure to chemicals, radiation, mistakes during cell division, and infections of viruses. And on the right here, I have an illustration of a normal DNA ladder and a mutated DNA ladder where the nucleotides are messed up. Since our mutation R553X is a cystic fibrosis mutation, I thought it would be important to go over exactly what a cystic fibrosis mutation is. And they are caused by mutations in the gene that produce the cystic fibrosis transmembrane conductance regulator. And this protein is responsible for regulating the flow of salt, chloride, and fluids in and out of the cells. So right here, I have a normal CFTR channel. And as you can see, the chloride ions, the little green dots on the bottom, they're able to exit and enter out of the cell. And the main job of the chloride ions are to attract water. And so as you can see, they're able to do their job perfectly there. And then on the right, we have a mutated CFTR channel where the chloride ions are not able to exit in and out of the cell. So they're not able to attract water. And that is what causes the thick mucus layer. And that is overall what the mutation is.
How does the mutation affect the function of the protein? R553X is a mutation class 1, the most common class mutation, with 22% of people with cystic fibrosis, CF, having at least one type of mutation from this category. The category includes other 2 types of mutations, which are G542X and Y1282X. All of these mutations are nonsense mutations, meaning they are a single point alteration in the DNA. R553X specifically is a stop mutation, which means no functional CFTR is created. In the chart next to it, you can see a lot of different classes of mutations. And in the next slide, we have the structure, the effects on the structure of the mutation. The nonsense mutation occurs in exon 11 of the CFTR gene and produces a shorter protein, which essentially just means it's reduced or is completely absent. There is an image to help you visualize this. The ribosome is the little ball, the Sasha might be, yeah, right there. It's a little ball that goes along the line, which is mRNA. It goes all the way on it with amino acids going in it and protein coming out of it, which is the curly little thing coming out of it. In the next slide, you'll see a picture that has the mutation, which is that red little thing on the mRNA. That causes the ribosome to come apart, and it stops it from producing more protein, which is fallen over there. It stops the function of the ribosome, and it's obviously a problem.
Okay, so now that we have talked about the effects of R553X on protein and protein structure and function, I would now like to talk about how CFTR is inherited. So everyone has a copy of the CFTR gene, one from your mother and one from your father. And for someone to have cystic fibrosis, there must be a mutation in both of the genes that are inherited. So right up here, I have an illustration. I don't know if you can see. Let me see. So right here, I have an illustration of a normal father and a carrier mother, and they have chances of having two heterozygous carriers, which doesn't necessarily mean that their baby has cystic fibrosis. They just carry a mutated gene for it. And then they have two homozygous normals. Now, if both of the parents are carriers, they have a chance of having two carriers unaffected. That means they don't have cystic fibrosis, but they do have a carrier gene. And then they have one unaffected child who doesn't have nothing, not the gene or cystic fibrosis. And then unfortunately, they have a chance of having a child who does have cystic fibrosis right here in the red. Okay, so now when we talk about the disease symptoms that R553X mutation has on different people, and me and Elizabeth actually found a very interesting case study where we talked about the differences and effects on Caucasian and Taiwanese patients.
Patients heterozygous for 353X, oh my God, R553X, it's specifically for Caucasian patients. 353X, oh my God, R553X accounts for 1.1% of cystic fibrosis chromosomes in the Caucasian population. The majority of these mutations have been identified in North American and European people. Most Caucasian patients who have this mutation are heterozygous for it, just like this section. There is little to not danger on their health though. Most of the time, it's almost like they have no symptoms.
Now when we talk about R553X in Caucasian patients who are homozygous for it. So there have only been 2 reported homozygous patients, and they both have very different symptoms at the beginning of their life. The first patient had failure to thrive at the beginning age of 16 months and later developed like moderate compromised lung function until they were 13 years old. And the second patient, for the beginning of their life, they were nearly asymptomatic and they had no sign of clubbing. And clubbing is clubbing of your fingernails, which is a very common symptom with cystic fibrosis. Both patients had later developed onset and relatively mild pulmonary involvement. And some of the symptoms of mild pulmonary involvement include pain in chest, dizziness, fatigue, chronic cough, swollen legs, etc. Now we talk about R553X in Taiwanese patients. And Taiwanese patients with our mutation have way more severe symptoms than Caucasian patients. Some of these include failure to thrive beginning at 2 months. I'm talking about 2 patients here who actually had the same effects. Both of them had failure to thrive at the beginning of 2 months, chronic hypophyxemia and pancreatic insufficiency at the age of 3 years. And later on, the patients deteriorated at a faster rate than Caucasian patients with a similar genotype. And why do they have more severe symptoms? It could be environmental factors or just gene pools. And then right here on the right or the left, I have normal healthy lungs. And then on the left, I have a Taiwanese patient with our mutation, and it shows their lungs and how unhealthy they are.
And this is the slide for the cure. Since there is not really a cure because our mutation affects only 10% of all of the patients with CF. And like Sasha mentioned with the Taiwanese patients, sometimes researches would take longer to have a cure because there's not enough people to make research on, and there's just a lot happening. And one of the most promising ways that hopefully in the future there will be a cure for this 10% is with a read-through drug, which we have another image to help you visualize. I hope the cameras are not on it, but there's a little purple ball on top of the image that we saw earlier. That little purple ball is the read-through drug, which would attach to the ribosome. And when the ribosome goes through the red part, which is a mutation on the mRNA, it will just read through it. It will technically skip it, so it won't stop. It will keep going and it will finish its job making protein. And that would hopefully make it like there was never a mutation, really. Slide.
Okay, so in conclusion, today we talked about what a genetic mutation is,
How R553X affects structure and protein,
how CFTR is inherited,
the effects of R553X on Taiwanese and Caucasian patients,
and some treatment options for the mutation R553X. And our hope for the future is that there would be a cure for the 10%. Thank you.
and we also have a works cited slide.
Oh, yeah.
next.
We do. In case you
And-
want to look more into our mutation, we have some sources here.
Okay, that's the end. Thank you.
Very good, guys.
Thank you.
Thank you.
Yeah, the slides you guys used, they were awesome. I hadn't seen those and looking through them. They were really good.
Yeah, I like the space filling models showing how the drug causes a read through right past the mutation. I hadn't run across any images like that either.
Well, I was saying thank you this whole time and I was muted. I'm sorry. Thank you.
Thank you.
That was very well explained too. A lot of things you learned.
Thank you.
Okay, that was group 9. Next we have group 10.
I don't know if there was any problem because I didn't hear Rachel. Rachel say anything. Rachel, are you here? She said she is not muted.
Oh, she's,
Okay, hi, I'm muted. I was muted. I'm sorry.
um,
I will share the screen right now.
Okay, take 2. Hi, everyone. I'm Rachel, and today my group is going to be presenting the cystic fibrosis mutation W1282X. And I will be presenting both the structure and function of a protein affected by this mutation. So to begin, there's a few classes that mutations fall under, ranging from mild to severe. In this case, our mutation falls under class 1, which is classified as a severe mutation. The structure of a W1282X protein is not at all that of a normal CFTR protein. As a nonsense mutation, a premature stop codon is added as a result of the mutation, hence shortening the protein and altering its original structure. Normally, the information from the mRNA is used to create CFTR by translating to protein and then so on and so forth. However, because of the premature stop codon implemented by the mutation, the protein doesn't produce effectively and will deteriorate before it ever makes it to the membrane. Because the protein is now completely non-functional, chloride ions will see little to no movement in and out of cells, thus hindering the free flow of mucus in its corresponding systems and resulting in the various symptoms of cystic fibrosis. Additionally, this mutation shows a greater severity of symptoms in patients homozygous for the disease.
Hi, my name is Weston Rafo, and I will tell you about the symptoms that is caused by the mutation W1282X. And as this is a more severe, I wanted just to turn off my camera. I don't know how now. Yeah. Okay. I'm not sure how I do it because I am just presenting the.
Okay, well, if you see a way to do
Yeah,
it.
I
Turn
do.
it on, but it's not essential. Now we see you. Yeah.
Yeah, I didn't know where is it. Okay. As this is a more severe class mutation, the symptoms will be more severe. The most common symptoms associated with cystic fibrosis that occurs with the W1282X mutation, one of them would be the mechanism ileus. The initial clinical presentation that diagnoses cystic fibrosis patient with the W1282X mutation is mechanism ileus. This occurs when mechanism, a baby's first stool, abstract the end of a baby's small intestines, also known as the ileum. This usually happens because the baby's stool is too thick to pass through the entire digestive tract. The mechanism ileus will affect, the mechanism ileus will affect 1 on every 5 newborns with cystic fibrosis and is rarely seen in those without mutations. Some other symptoms that this mutation would associate with is respiratory illnesses. The most common symptoms for cystic fibrosis are coughing and chronic breathing difficulties caused by the buildup of sticky mucus in the lungs and respiratory tubes. That also leads to lung infection. Chronic lung infection are very common, and in long term, this can result in a lung scarring called fibrosis. The damage caused by this fibrosis and thick mucus damages the airways of the lungs. In turn, this leads to a tendency toward more infections and decreased lung functions. Another one, which is one of the most common, is pancreatic insufficiency. It's enabling to digest food caused by the thick mucus blocking the pancreatic duct. This prevents the pancreas from delivering enzymes needed for digestion due to the pancreatic extrinsic insufficiency. Also, it's like children with the pancreatic insufficiency suffer from malnutrition, which leads to slow growth. Also, pancreatic insufficiency can result in impaired insulin secretion and carbohydrate intolerance, leading cystic fibrosis-related diabetes mellitus. And with this pancreatic insufficiency, 85% to 90% of people with cystic fibrosis have pancreatic insufficiency, which is common even in a young age. The complication beyond these diseases can affect other organs and life expectancy. One of the last one that I have is infertility. Cystic fibrosis affect reproductive fertility, particularly in males. Approximately 98% of males with cystic fibrosis has congenital bilateral absence, sorry if I'm spelling it wrong, of the vas deferens, blocking the transport of sperm and resulting in azoospermia. But infertility in women with cystic fibrosis is not as common because many women can have it and even have babies. And all these data I have them from cysticfibrosissources.com. And now I will leave you with my another partner, Leonardo, to talk about the treatments or cures.
Thank you, Wasan. Can you guys hear me?
Yeah, I can hear you fine.
Okay.
Yes, we can hear you.
All right, thank you. Yeah, I'm going to talk about some treatments and cures available for the symptoms caused by W1282X mutation. There's lung transplantation medicine, ACT, which stands for airway clearance techniques, and gene manipulation. There's more options available, but these are some of the most important in my opinion. And then could you go to the next slide, please? Thank you. So a lung transplant is typically done when the lungs are simply too damaged via scarring to properly function, even in combination with other treatments. Depending on the severity of the patient, one or both lungs may need to be replaced. Something very interesting about this treatment is that the lungs will actually no longer have cystic fibrosis symptoms. Of course, the disease will still be present in other parts of the body where cystic fibrosis manifests. One side effect of organ transplants is that the patient will be required to take immunosuppressants for the rest of their lives in order to prevent organ rejection. And as the name implies, immunosuppressants reduce the immune system. And so for someone with cystic fibrosis who already may have a reduced immune system, the risk of fatality via infection increases greatly. There are many different types of medications used to treat cystic fibrosis. However, most are introduced to the body via inhalation using a nebulizer. The most common of these is a mucus thinner, which helps the respiratory system remain cleaner. There's also infection suppressants, so something like antibiotics will be used to try to prevent someone from getting very sick. Something quite nice is medication which performs something known as CTFR modulation. This basically attempts to correct the malfunctioning protein at a cellular level, thus potentially slowing down the effects of the disease. Something more traditional that would be used is airway clearance techniques. These include huffing, which is a type of coughing done to clear mucus in the respiratory system. There's also chest physical therapy. This involves applying pressure in waves to the rib cage with the use of hands to essentially move mucus up the trachea. And there is a more modern technique of this, which is something called a high frequency chest oscillation device. It's basically just a vest someone wears that vibrates and does the same thing, but just more efficiently. And lastly, there is gene manipulation. This is probably considered to be the most effective treatment or cure, using the Cas9 protein gene editing tool, also known as CRISPR. One can fix the mutation of the DNA of cells present in the body. And there's two ways to go about this. One is treating the airway cells in existing patients. And this works, but due to the slow reproduction rate of airway cells, it's not super effective. The second way is actually to correct the mutation at a very early stage in embryonic development. This is known commonly as creating a designer baby. And it leads to an adult human with no cystic fibrosis present in any cell in the body. So essentially a cure.
So in conclusion, the 1282X nonsense mutation is a very severe cause of cystic fibrosis that result in various symptoms as mechanicum, ileocyst, respiratory illnesses, lung infection, and pancreatic insufficiency and infertility. While possible treatments such as lung transplant, medication, airway clearance techniques, and gene manipulation should be considered, improvements in technology with vessel improve for ability to reduce the impact of the mutation and life expectancy. Thank you. If you have any question, please just tell us.
Okay. Any questions for group 10?
I just had the one, when you said mucus thinner, is that like blood thinner?
Yeah, similar. It just makes it less viscous.
Less thick, okay.
Yeah.
Okay, thanks.
Okay, anything else? Comments? All right, thank you, group 10, and we'll go on to group 11.
Can you see it?
I can see your screen.
All right. Everyone, 1 second.
Do we have to share our camera? Right.
Prefer it.
No, my camera's not set up right now, so okay. You ready?
Yeah, we're ready.
All right. So our group is group 11 presenting the mutation G542X, and I'm Ian Davis.
Yusa Dali and Anthony Arbach.
Okay, so this gene codes for the protein cystic fibrosis transmembrane conductance regulated protein. It's a ABC transporter class ion channel responsible for chloride thiocyanate ions across the epithelial cell membranes. And the gene itself was identified in 1989 by geneticist Lapsji Sui and his research team. It's found in the lungs, liver, pancreas, intestines, reproductive tract, and skin. And it's composed of 27 exons that encode its genetic sequence. It's found on the chromosome 7 on the long arm at position Q31.2. And then for the CFTR mutations, the mutation is among the class 1 mutations, which is nonsense mutation in exon 11. The mutation itself has a 2.4% prevalence worldwide, and it's the second most common in the CFTR gene after delta F508. It causes CFTR proteins to not be synthesized. Its defect type is no protein, and it leads to a decrease in sodium chloride transport and sodium thiocyanate in the ducts of sweat glands, leading to cystic fibrosis. Sorry. The effect it has on protein structure and function. The CFTR protein belongs to the ABC ATIP binding family of proteins. It is composed of 5 domains that include 2 MSDs, which are membrane spanning proteins, 2 NBDs, nucleotide binding domains, and a regulatory domain. When the camped CFTR channels become activated, it causes increase in conductance for certain anions to flow along the gradient. This protein functions as regulated chloride channel, which regulates sodium and chloride channels along the surface of cells. The NBDs control the channel grading by ATP hydrolysis. And that's it for this one. mutation itself, the class 1 mutations can be caused by nonsense, frame shift, or splice. Site mutations. These mutations leads to the formation of a stop codon that's leading to a premature termination of the mRNA. I think I took one of my group mate slides, maybe. Yeah.
Yeah,
I
that was
did.
supposed to be me.
Yeah,
Okay.
sorry. Oh,
All right, did you finish reading this one?
yeah.
All right, you can get to the next one.
Oh, okay, I'll finish reading. Okay, so, mutation will cause a stop codon to be formed, and thus it's a nonsense mutation. And it causes the protein not to be made, and thus it will not be formed. That's it.
All right, this picture represents a mutant versus a wild type. So on the left, it's a picture of a normal CFTR protein, and on the right is a nonsense mutation caused by the lack of CFTR. Next slide. All right, cystic fibrosis is autosomal recessive. It affects the lungs, pancreas, liver, and intestine. An abnormal transport of chloride and sodium causes the secretions to be thick and viscous, and which causes multiple complications. This phenomenon leads to scarring and cystic formation within the pancreas. Next. Some symptoms of the mutation can be difficulty breathing caused by infections in the lungs, salty taste of the skin, increased secretion of thick and sticky mucus, an increase in infections causing dyspnea. Among males, it causes infertility, which is because of the absence of vas deferens. These symptoms are more common in infants and children, but they're more severe in adults.
For the diagnosis, the diagnostic criteria for cystic fibrosis are clinical symptoms of CF in at least one organ, or positive newborn screening, or having a sibling with cystic fibrosis. Another is lab testing, such as sweat chloride test, which is a primary test of diagnosis. For the treatment, treatment to clear abnormal excess secretion and treat infection in lungs. Prevent obstruction in intestine. High calcium and protein diet is needed. Another diet is one in low fat and high in sodium. Chest physiotherapy is used to improve respiration. Aerosols and mucolytics. Another treatment is a lung transplant in advanced stages of disease. Aminoglycide antibiotics helps overcome premature stop mutations. For the genetic treatment, gene therapy is a way to cure cystic fibrosis by replacing the gene before the disease causes permanent damage and morbidity. Another treatment is gene therapy, which cannot repair organ damage that has occurred. It only works on cells that have received the therapy. In conclusion, cystic fibrosis is the second most common cystic fibrosis mutation, which is G542X, is the second most common mutation. Its possible cures are in the process of being researched on. Thank you for listening, and that was our presentation.
Cool.
Okay,
Any questions?
questions or comments for group 11? Hearing none. We'll go on to the last presentation by group 12.
Yay, group 12.
You get the honor of going last.
Woo, yeah, save the best for last. All right, I'm gonna share my screen. Da, 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 da. Yes. Is timer starting now, or like
Time is starting
in 10
now.
seconds? I mean, good morning, everyone. Today, Manny and I are going to speak about cystic fibrosis. More specifically, class 5 mutation. Our that includes our gene 2789 plus 5GA. Okay. So what does a koala, what does a koala, you and Tom Hanks have in common? Well, we are all made out of cells. These cells are a subunit of life. Inside the cells, there's a nucleus which contains our DNA. In this illustration, I'm going to show you DNA strand. And that's what's called the nucleus. The DNA includes the adenine, guanine, cytosine, and thymine. Each of our cells contains genetic information that provides the body with coded instructions to make proteins, which determine how the body looks, develops, and works. So this relates to cystic fibrosis because when there's a genetic malfunction, things happen, and what's it called? And there's splicings involved. Splicings are a missing segment of a what's called strand, which has an unnecessary segment, a missing segment, or a cut segment. Okay. So this affects your CFTR mutation on the protein structure. Spike mutations interfere with the ability of the cell to correctly read the instructions for making the CFTR protein. So on this illustration right here, you can see it shows how a protein is made from DNA. So the amino acids are the folded forming a protein, which to the cell membrane, the protein is a channel that needs to open and allow ions to flow through. Exons and entrants are translated into amino acids. So getting back to cystic fibrosis, the splice mutation interfere with the ability of the cell to correctly read instructions for making the CFTR protein. This affects the protein structure by creating a limited amount of CFTR protein, making a small number of protein at the cell surface that works correctly. The protein at the cell surface degrades too quickly, leaving small numbers of protein behind. Our class 5 mutation, it's what that malfunction does to the CFTR protein. On this video, I'm going to show you a little bit about it. Well, there's no sound, but I'll narrate it. So the production of CFTR proteins. Oh God, that was fast. Sorry guys. Oh God, no. Just disregard that. Okay. So the point was that there wasn't enough protein, and there wasn't insufficient quantity of normal CFTR protein at the cell surface due to alternative splice mutations. So it didn't reach the top. So the effect of your CFTR mutation on protein function. If the CFTR protein does not function properly, it causes an imbalance of chloride in fluids, causing mucus in various organs to become thick and sticky. This leads to lung infections and eventually respiratory failure in the lungs, poor digestion, and problems in the reproductive system. And this video, it shows a little bit of that. The mucus is on the surface and inhibits their job.
Alrighty, so what are some disease symptoms for this mutation? Compared to other mutations, symptoms are mild. And there was a study done on a 6-year-old boy. So what they found in him that they didn't find any symptoms in his pancreas. He wasn't having any digestive issues with his enzymes. The only thing with him was he was showing a respiratory illness, so bronchitis. He had bronchitis 3 times within a 3-year span. So every year he had bronchitis. So cystic fibrosis increases that, those infections to accumulate over time. And then on the image on the right, we'll see that the respiratory system, like I said, is coughing, the thick mucus, shortness of breath, and chest infections. On to the next slide, please. So in order to actually find out if the boy had cystic fibrosis, we have that image on the right. That's called the sweat chloride. It's a pilocarpine ionophorus sweat test, and that's to determine the level of chloride within somebody's sweat. So anything that's 20 and below is considered normal. Anything that's 30 above or 30 to 40 is like suspected. So they run numerous tests. And then once you reach that threshold of 60, it's where you're usually diagnosed with cystic fibrosis. And anything above that, it depends on your class of mutation. So you see like at 60 and 80, you have classes 4 and 5. And then it goes even higher when you go to class 1 and 3. So that's why those symptoms are even worse in those classes. And then that image on the bottom right kind of shows how that test is done. And you'll see at the very bottom, I know it's hard to see, but you'll see that the chloride ions aren't passing through, or there's too much chloride within the sweat at the very top of the course. All right, next slide, please. So you have potentiators and amplifiers. I'm gonna talk about potentiators first. We all heard about the Kalydeco or the Vica factor that allows the channels to remain open so that chloride ions are allowed to pass through out of the membrane. And then there's also another one called genistein. And it's pretty much the same thing as the first potentiator. And I'm gonna show you guys, or Jose's gonna show you guys a video of what that looks like, or how it actually works. The second video, yeah, that one. And it starts at 7:50.
Seems there's no sound.
So what the guy's talking about is there's no sound. He's just pretty much clarifying what I just talked about, like those channels not enough CFR, not enough protein being at the channels. So instead of producing more proteins, what it does is allows to keep those channels open for a longer period of time, which eventually allows more chloride ions to go through those gates. Go back to the slides, please, Jose.
Okay, this one?
The next one, please. Okay, so and then we talked about potentiators. We also have amplifiers. And what amplifiers do is they increase the CFTR protein levels within cells. And so that allows us to create more CFTR proteins. So with our mutation, we don't have a problem with our protein being abnormal. We just have a problem with not creating enough. So amplifiers would definitely work with this type of mutation. And I know the pictures are hard to see on the right, but the bottom right picture which says what do amplifiers do? In the very right of that picture, you'll see that they do a combination of amplifiers and the potentiators. So there was a phase 2 clinical trial with amplifier PTI 428 and a combination of Lumica factor and evaca factor, and they showed an increase in lung function. So amplifiers themselves aren't necessarily a good treatment. They have to be combined with other treatments as well to see the maximized benefits. And then Jose, you can finish off with the conclusion.
So in conclusion, disease symptoms for this mutation are milder compared to other mutations, and patients show symptoms in the respiratory system and sweat. Treatments for the disease include potentiators in the future and in the future a possible amplifier. As Manny explained, amplifiers help the production of proteins to reach the top. And yes, thank you for listening.
Okay. You have the distinction of not only being the last presentation, but managing to work in both koalas and Tom Hanks in the same presentation. So that was good. Okay, well, I want to thank you all for your presentations, both today and the ones that were on Monday. And I'm very impressed with what you've all done. Particularly, you've all talked about the same disease. And so obviously there was a lot of overlap, but each group managed to work in some unique information. And I found that both resourceful and interesting. So we're almost out of time, so I'll keep my comments to a minimum. What I hope you were able to get from this is, from this entire exercise, was the opportunity to, first of all, focus on a particular question and do research on that, then organize the information that you found and prepare illustrations to show an audience what you had found in a way that could be readily understood. And then, of course, organizing the presentation itself. I think all of the groups did a good job of that. I appreciate all your efforts. I know that you worked hard. Each of the groups put in a lot of work, a lot of time. That's obvious from your presentations. So thank you for that. And I appreciate your efforts.
Professor?
Yes.
I missed my presentation on Monday. I was wondering if I could do it right now at the end of class.
I'll keep the Zoom open, and the class period is up, but go ahead, Samuel, and do your presentation.
Hello? Oh, okay. I'm trying to unmute myself. So my camera's broken, so sorry, I can't turn it on.
Well, I can't see your picture, but I do see your screen, your slides.
Oh yeah, my camera broke on this laptop, so I'm sorry. All right, hello, my name is Samuel Rodriguez, and I'll be presenting on the R347P mutation. So the effect that this mutation has on the protein structure is the first thing I'll be talking about. So it's a class 4 mutation, which means that it's the channel of the protein that's affected. So CFTR proteins will still be made and they will still reach the cell surface, but because the channel is faulty, it makes it difficult for water and salt to leave and enter the cell. So basically there's a decrease in efficiency of the protein, and this is what causes the buildup of mucus. So in this illustration I have, on the right side, you can see like normal CFTR proteins. And then on the left side, it shows you the different classes, but on the top in the middle is the class 4 one. So as you can see, it's still at the cell surface, but compared to the normal ones, it looks abnormal, and that's because the channel is affected. So where is this where's the R347P mutation located? It's on the long arm of chromosome 7, and this picture I added shows you the more specific place it is. So it's under the TMD1 section, and it's on the 7th exon, along with 2 other mutations. Thank you. I just had those 2 slides.
Oh, okay. All right. See. Okay, you can stop sharing your screen. And thank you, Samuel. And the class period is over. So if there are any comments or questions in overtime, speak up. If not, we'll go to next Monday. We're going to start a whole new topic on production of energy by biological systems. And also on Monday, we'll go over the answers to test 2, since we haven't had a chance to do that yet. Okay.
Okay, thank you for your patience with us. Thank you.
All
Excellent
right.
job, everybody.
Thank you, Professor. Have a good weekend.
Okay, you too, everybody.
Thank you, guys. Have a good
Bye-bye.
weekend too. Bye.
Bye. I'm going to end the session.